Hey, how's the audio? Good. Good. So let's pick up from where we left off on Wednesday. So we were now looking at sort of practical examples of operating system execution models. Now that we've sort of got a bit of a background in various execution models that we might utilize to implement an operating system. And I'll recap on this particular example again, just to get us warmed up and to get me warmed up, where we have some sample code that invokes a some kind of primitive. Guess what's gonna... Whoa.
Still playing us?
Yeah, you remember Extended, do you?
Oh, yes.
With the live streams? I didn't do it yesterday. I hope it doesn't haunt me for the rest of the lecture. Let's try again. Okay. How's the live stream? Did it pick it back up? Good. So what we've got here is the per thread kernel stack model, where we have the standard kind of execution model where we have a thread of control that's executing from start to finish, i.e. the top to the bottom of the slide. And we've got this sort of weird bit of code that tests whether the next bit of code is going to block. And that's mainly there to be used as an example later on for the other the other models that we're going to look at. But just quickly recapping on this particular model, we get two arguments to this function. It invokes some function using those two arguments. Then it tests to see whether this section of the code will block. And if it is going to block, it goes into that part of the code, blocks for some period of time, and then eventually the function that blocks returns transparently back to this location, and we as the programmer don't really need to consider what's going on, what happened inside that function that resulted in blocking. Like this could have been a synchronization primitive, it could have been the attempt to acquire a lock, it could be any primitive that resulted in suspension of this thread for some period of time, and then continuation of this thread when that particular function blocked. Once it returns, we invoke P2 with that particular argument. We don't do P3 because we're not interested in the non-blocking case, because that's not the interesting part of this example. And then we flow through and we return from the example success. And again, like I said yesterday, the main point here to take away is that with the multi-threaded model, i.e. with the per thread kernel stack, our execution model is from start to finish, and any saving of state required to suspend in order to block and then later restore to resume is implicitly managed by the model on the kernel stack. Okay. So any queries now that we're back to where we were? Whoop. Okay. So let's have a look at the alternative, the single kernel stack model. Basically, how do we use a single kernel stack to support multiple activities at the same time? So let's use sort of the OS 161 standard kind of Unix model as an example here, and rephrase that question slightly. How do we support multiple processes running on top of the operating system when we only have a single stack inside the operating system to support effectively all the competing concurrent activities that processes are requesting from the operating system? And that largely ends up boiling down to how do we end up supporting system calls that can't immediately satisfy the request and return back to the application, i.e. system calls that block. So we have two choices. One is that we can use continuations. And the other is we can use an event model within the operating system, which is sometimes called the stateless kernel. Because once we don't have state stored within the operating system on a per thread basis on an implicit stack. And as I pointed out yesterday, the classic sort of comparison between the stateless model and the stack per process or stack per thread model is this paper on the Fluke kernel where they built an API and an operating system where they could configure a single stack implementation and a multi-stack implementation, and they did a comparison between the two. And this is what SEL4 happens to be in the model we chose, which I won't quite delve into the details yet. So let's have a look at continuations and how this might work. So the state required to resume a block thread is explicitly saved somewhere, okay? So what we're doing is we need to use this model, we need to be able to, and the implicit assumption here is that we're using C, and I'll use that as an example. We need to explicitly identify what state's going to be needed in the future in our program, and we need to identify where we would like to restart in the future as we are programming along, okay? And the reason why we're doing this is that the stack can now be discarded and reused to support effectively the next system call from the process. Or in the case of the project, the next incoming IPC for your simple operating system from the next client that you're servicing. Okay, so in the project, you're going to have to come up with a way of effectively recording the progress that you've computed thus far on behalf of one client in order to be able to receive the next request from the next client while that any I/O or any other kind of asynchronous activity can complete in the background. Okay. So let's have a look at this particular model using the example that I introduced last time. Okay. So we've got the same example here that takes 2 arguments. Okay. And we're using a continuation-like model here, where we call the example, and we again call that function with the 2 arguments like we did last time, because the arguments are basically passed in and we have them. Then we test to see if we're going to block again. And now, since we know that we're going to block, and if we block, all the state that's encoded on the stack is going to be lost, because if we block, we're going to switch to a different activity that's going to reuse the same stack. So now we have to explicitly identify what we need to use in the future and where we would like to go in the future. So here we've chosen the thread control block as to where we're going to save our state. And so this sort of pseudocode-like thing on the slide is implying that we're going to pick the argument that we need in the future, which was the argument for P2, which was arg2 originally passed in. And we're going to store it on the TCB. So in this design, it's kind of implicit in the way it's described here, that each sort of continuation associated with a TCB it can only be blocked at one time, okay? Or, because we've only got space there to store the argument. We can't basically recursively sort of block multiple times on the way, obviously, because we can only sort of suspend once. So once we've saved the state that we need in the future, we can then call our thread block routine, and we pass in the continuation, which is the function pointer, of where we would like to start running when thread block results, or when the thread basically is unblocked. Okay? We've got a single thread of execution in the system, and we're using this continuation to suspend it in order to be able to process another activity. If we weren't going to block, we'd just run P3 as usual, and then we'd run a different function rather than return directly. What we've done is we've called an explicit function here that returns success to wherever success is meant to go. So this might be the return code for a system call. It might be the IPC arguments for a return. And this particular function throws away the current stack and environment such that when the next request comes in, it starts on a fresh stack. Okay. So the exact implementation of this is kind of really dependent on the environment that it's used in. You can imagine if you're on the bare hardware and I'm using OS 161 as an example, and I'm assuming that you have at least a vague recollection of the system call kernel entry path on the MIPS hardware, where a system call instruction generates a trap into the operating system, and the exception handler, the low-level code that takes control at the point where the hardware gives software control, one of the things it does is it sets up the stack again for safe execution of C code. So effectively it starts with a fresh stack on kernel entry every time. Where this model differs with the single stack versus the multi-stack is that in the multi-stack, we basically set it up so it starts afresh on that processor's particular stack. In the single stack case, we start afresh on kernel entry with the same stack every time. Okay? So anyway, let's rewind back. When thread block actually unblocks, we don't return back to this code because effectively the state associated with the point of execution no longer exists. Example continue gets called by the machinery that implements thread block, and example continue grabs the state that we saved that's required to continue, invokes P2 like it would have in the previous model, and then again calls syscall return success, which arranges for us to return back to the original process that triggered the system call in the first place. So any queries at this point?
So it may be completely relevant to the, I get the continuation part, but with the like P2 versus P3, they're meant to be like different functions. So it's like if it blocks, it does one thing.
Yeah,
right.
yeah. It's just a toy example. The main takeaway from this is the idea that if we're going to block, we need to come up with where's it going to go to when we're unblocked, and what state are we going to need in the future to be restored in order to continue the processing that we require.
And for the arguments that would say in TCP, would that be always all of them, or sometimes just like I know that I only need these three?
Super good question. The challenge with this particular model is that you need to save everything that you can potentially need to use in the future, okay? And that might be really simple, like in this case here, it was really trivial. It might be relatively complex to identify what the state happens to be in order to be able to continue it in the future. And the challenging part to this is that you have to be conservative in that you need state for all the potential paths that you might branch out into if this is complex code. So this model gets challenging to program as the level of complexity increases. Okay? You don't want to create too much of a can of worms by having a very complex model with lots of state around that you have to effectively save into a continuation in order to restore it, when only a small fraction of it might only end up being used in the common case. Okay? Okay, so for the stateless kernel, by definition, system calls are not allowed to block inside the kernel. Okay? Every system call that can't complete because the resource is unavailable takes the strategy of modifying the user state such that the system call is tried again when the resource is available for the system call to complete. Okay? And that allows the stack content to be discarded inside the operating system. So rather than effectively, I'm going to probably end up hand-waving the example coming up on the next slide. But one way to think about this is that typically a read system call is going to grab something that might not be available, and you're familiar with the code path that we were using in the assignments last term, where the read path would basically, we'd enter the operating system, we'd figure out that we're doing a read system call, we'd go through a whole lot of code through the virtual file system, we'd finally get into the file system that actually understood the disk, and then we finally issued a request to the disk driver to give me a block, and it would block at that point deep in the code, okay? And then we'd switch to a different stack, and eventually we'd get the disk block and read would continue. In this particular model, if we don't find that we can complete the system call in a scenario like that, we effectively unwind all that execution that determined that we're going to block on the disk request after issuing the disk request, and then arrange for the system call to restart that read again in the future when the disk block is available. Okay. Now the challenge in doing this is that the level of complexity and nesting depth to determine that we're going to block ends up making this fairly complex to rewind and restart and inefficient to rewind and restart in situations where the kernel is quite complex. We can't really have a paged kernel, okay, because it's very hard to unwind. In theory you could, but it's quite challenging to unwind a kernel that takes a page fault on some memory that's missing, then service the page fault and then restart the whole thing so that you effectively hit the same point and find that the code's actually in place or the data's actually in place the second time you run the system call. Okay. So let's have a look at an example with some more complex code. This is actually an example from a previous generation of L4 where there were a few different variants of that kernel in prior to SEL4, and we were looking at the message passing path and whether to use continuations versus a per stack. A stack per thread model within the microkernel itself. So I should introduce this particular example so that then we can talk about it. Okay? So what we've got here is a message send and receive combined together for efficiency reasons. Okay? So this is the typical send and wait for a response. But the particular variant that I've chosen to have a look at here, it makes the assumption that the send always succeeds, i.e. either it's a notification-like send, which is asynchronous, which is always successful, or the assumption here is that the receiver is always ready. Just to make this example a focus on the part that I'm more interested in. Okay, so here we basically are doing a send-receive. We've got the message that we're going to send and or a description of it. We've got a send size, a receive size in this particular primitive. We send the send part of the message. That succeeds. We check to see whether that was successful. If it was not successful, then we should simply return an error code back to the original core of this function within the operating system. If we were successful, then we do the receive part, and given we just sent, we're going to be waiting for the response, and so this will block. Okay? So this particular message receive will block until we get a response. It has the arguments that it needs for the function to provide the buffer required for the response for that particular message. Once we get the message, we return whatever the return code happens to be for the receive part of this message. Now, the thing to note here that I'm focusing on is message receive happens to be a blocking operation because we may not have a message to receive yet from the request that we made in the send part. Okay? But however, the way we've written the code, we don't have to worry about that because we've got a per thread stack so that we can simply write the code, and any state that's required to be stored while this particular component, the message receive, is suspended, is implicitly recorded on the stack. Let's have a look at the continuation model. Okay, same message receive, same set of arguments, same send that we're going to assume always succeeds and never blocks. And then same check. Let's assume that we've got a successful send. Now we're going to call a message receive that is potentially blocking. Okay, it may not succeed. So what we have to do is conservatively save the state that we might need to continue the receive when there is a message available to receive. Okay. Then our message receive is slightly modified to specify the continuation, i.e. the continue point of what gets invoked when there is a message ready. Message continue restores the state that we need to do the message receive and tries again. Note if it doesn't succeed, basically comes back and does this again. Okay. So what we've done now is we've freed the rest of the framework of execution from needing to preserve the stack for this particular function. If we block inside message receive, the underlying blocking primitive can throw away the stack and accept the next system call into the operating system, which might be the send that's providing this message. And if that send identifies that, yes, this is the particular target for that particular send, then it can invoke message continue, and it basically pulls the state out and does the receive for the original request all. Okay? So you can see that with this model, you as the programmer are forced to think about the state that's required in the future, identify it, store it somewhere where you can get it back in the future. Let's have a look at the stateless kernel model. So again, same thing is happening at the start of this. We do a send, request something, it succeeds. And then we do a message receive. Now, given that we can't block inside this OS, if we can't receive a message, we need to do something. And so what we do is we signal that we would block. Okay? Now, if we would block, we need to do something about that. Okay? So what we do is in this example, we set the current thread's program counter for kernel entry to be a slightly different function than send and receive, we set it to call just receive. And then we return back to the underlying framework that called this function in the first place, and what it does is it finds something else to schedule, because we've indicated that you should schedule somebody else, because we will be able to continue at some point in the future. But when we are restarted in the future, we don't start the same system call, because effectively what we've done is we've modified the request from the user such that it only requests what it needs based on the progress that was already made, because the send already happened. If we simply restarted the whole system call again, we'd send the message twice, okay, which is not what we want to do. Okay? So effectively, at a high level, what this stateless kernel is doing is figuring out the progress that's been made in the system call thus far, and it may actually be nothing yet, and we can restart the whole system call itself easily without having to do anything too clever. Or it's modifying the original request to take into account the progress made thus far. So you can imagine another example might be I'm reading from a buffer and I've got half the data that I'm looking for, so I could set it up such that I perform the read request again, but the read request is modified to basically request the second half of the buffer, because I know that I've already got the first half already. Okay. So, summary. Single kernel stack per processor, because basically we're talking uniprocessors at the model. Uniprocessors at the moment, let me speak properly. The event model, if we do that, then we need to deal with blocking. Okay, either we deal with blocking via a continuation, which has been used in various systems of the past, or we use a stateless kernel model, which is very challenging to implement, because not being able to stop or interrupt while you're running within the operating system puts a whole lot of requirements on the structure of the system, and what you can and can't do in order to be able to have this effectively atomic system calls, such that you never stop on the stack. Okay? And so the stateless model is what SEL4 mostly implements. Okay? There's very few situations where we don't effectively push the progress of SEL4 back to the register set that came into the kernel from the application. Okay. Right, any questions at this point? Nope. Okay. Now the big advantage of this model is that it has a low cache footprint. Okay. Caches are a limited size, even though they're basically getting bigger as technology improves. They're not getting bigger that much faster. And so the smaller the cache footprint of the operating system, which if you think about it, the operating system doesn't really do anything that the application is providing, okay? The operating system is just providing the framework for the application to run in. So the less hardware resources that the operating system uses, the more hardware resources are available for the application to perform its job faster, okay? So only using a single stack in the kernel, reusing that stack on every kernel entry improves your performance.
That's for both continuation.
Yes. Yep. So with the other model, it's quite simple if you've got a large complex system. So the stateless model and the continuation model is more applicable to small, let's say, microkernels, because that's what a particular focus of this course, where you can keep the system simple enough to be able to either have the atomic syscall model or manage continuations in a tractable way. Once the level of complexity gets really large, then those typical sort of general purpose operating systems that you're mostly familiar with, that have the millions of lines of code, they tend to use multiple stacks, i.e. a thread per process model, so that they can effectively execute nested function calls deep into the operating system, find that it needs to stop, suspend execution or synchronize, or wait for some other activity to occur, and then resume, without you as the programmer having to understand how the whole system pieces together in minute detail in order to be able to do something like continuations. Okay? And so you don't really have much of a difference between the programming model that exists between the kernel and user mode. In some sense, you've basically got this single thread of execution through a specific thread of execution through an application that just transitions into kernel mode, and it's a thread of execution within the kernel on behalf of that particular application. Okay. And as I said, most of the bigger general purpose operating systems, in fact all of the ones I can think of, all use this particular model. But it has the larger cache footprint, consumes more memory, which might matter for an embedded device. And that is the end. Okay, good. Okay. How are we doing time-wise? Probably went a bit slower than I wanted to. So here's what I'd like to go through now is I've given you the background to have an understanding of both threads versus events. And there's one particularly famous talk, which is this one, arguing that threads are a bad idea. Okay? And there's another talk that came out probably almost 10 years after this one that argues that events are a bad idea. And what I want to do is represent, hopefully do justice to both these talks, to give you more idea about the trade-offs between the choice of the two. Okay. Now, this is a particularly well-known talk by John Oosterhout. For those of you who did extended last term, you might remember the name. He was from the log structured file system paper as well. Okay. He's been fairly prolific in the field over the years. TCL/TK as well. So those of you who hate Xmark, you can blame John for coming up with that scripting language that Xmark has written in, for those of you who have done tutoring for the school. So, and this talk also got a mention again recently in the Distinguished Lecture Series that was on about 2 weeks ago. Butler Lampson also explicitly called out this talk in his case for keeping things simple. Okay, so I will skim relatively quickly on some parts because you've had probably 2 hours now with threads and events, so a lot of this background is going to be fresh in your mind. So threads, what are they? Threads basically came about as a way of managing activities of processes inside the operating system itself. Okay, took quite a long time in computer science for threads to be an application level abstraction that people expected to be able to use. Really an operating systems tool for OS writers who were generally gurus. Okay, they evolved into a user level tool, and they end up being proposed as solutions for a variety of problems that I've already kind of talked about. Managing concurrent activities, overlapping I/O with execution, etc., etc., etc. So that basically means every programmer should be a threads programmer. That's the question. Okay. Now, the challenge with that is that threads are really hard to program. How many of you, well, I suspect most of you, have banged your head against the wall with some kind of race condition that happens intermittently, that you couldn't reproduce, that you couldn't find out what was going wrong. It's challenging to basically program the thread model. Okay? There is an alternative. I've introduced it, events. And this claim that he attempts to make in this talk is that for most purposes proposed for threads, events are the better option. okay? Threads should only be used when we have true CPU concurrency, okay? Which, if you think about it, that's true everywhere now. Like, you can't even buy a mobile phone that has less than 4 CPUs in it, okay? But I will postpone that because in some sense you could argue that you run 4 event loops on a 4 CPU machine and you can keep it busy and avoid some of the synchronization issues. But I don't kind of want to go there. I want to assume a uni processor for the sake of this talk. Okay? Because a lot of the arguments basically still hold. So I don't want to prematurely, discourage you from being open to the ideas in this talk by saying, everything's a multiprocessor now. The ideas are still mostly relevant. So what are threads? I definitely don't have to introduce this. Okay, threads are basically independent sequence of execution that operate on shared state. Okay, they're preemptively scheduled, so we don't know who's going to make progress next, when they're going to make progress, and that creates race conditions where we need to actually use synchronization primitives of various forms that we all know now, because we've done operating systems, locks, conditions, monitors, etc., in order to manage that concurrency in a way that allows us to write correct code. What are they used for? Okay, we've all seen the operating systems case. They're actually, in the case of actually trying to keep CPUs busy, the classic one is scientific applications, where you've got your giant matrix multiply, you've got a machine with 1,000 CPUs in it, and you want to keep all those CPUs busy doing their little subpart of the giant matrix multiply in order to understand what the weather is tomorrow. Okay? Then, yes, you need threads to spawn off that work. Okay? But that's not what this talk is about. Distributed systems, where we want to overlap I/O with execution. And GUIs, where you want to keep different parts of the GUI responsive when you may have one part of the GUI playing a long-running video. Okay? Just because you've got a long-running video in one part or an animation in one part of the stream, that should not cause you to lock up the rest of the GUI because your video is running in an event handler. Okay? So what's wrong with threads? And I still love this slide. Back in 95, Visual Basic programmers were still frowned upon. Okay? We all can probably agree that programmers have different skill levels, like anything in life. And some areas or some application domains may be suited to a more broad range of skills. Trying to be politically correct here. C programmers tend to need more skills than sort of managed languages that manage most of the errors out, or compilers that tend to give you a lot of information before you even get a chance to run your code. C++ is basically all the problems of C plus more. Any language where you've got to pull out a book to understand some arcane syntax constantly can't be helpful. But the main point from here is that to program in threads, you're not down that end of the slide, you're way up here. Okay, skillful threads programmers require to be highly skilled individuals in order to be able to deal with reasoning about not only what's happening in the program correctly, but what's happening in the program at the same time by multiple activities that you have no control over the order of and the progress. Okay? So the argument here is for most programmers, which is everybody else, threads are actually too hard to use. Okay? It was a flurry of research activity in the early 2000s when the industry realized that, okay, we're all going to pile on this multi-core bandwagon and everything's going to go parallel, but no one's going to be able to program these machines anymore because the programming language environment is too hard. And so there was a lot of research into how to encapsulate parallelism in programming languages in ways that made it easier. But at the low level, the operating system runs in a low-level language with a minimal runtime to basically build up the environment so that these more high-level languages can exist. So we're still down here. Okay, so we're not going to solve this problem by jumping on some kind of new parallel language that, like say Rust, that makes race conditions exceedingly difficult to program. Okay, and so even for experts, development is painful. We've all debugged parallel code, and I don't think anybody's going to argue that it's easy. Okay, so why is things hard? First thing is synchronization. You've got to coordinate access to shared data with locks. If you forget a lock, the data gets corrupted. You don't notice because the code works reliably for the first 10,000 iterations, and 10,001 it fails for some reason, but you're not sure, and so you run it again and it works. And it keeps working until it fails again when you least expect it. Okay? And so that is challenging to deal with. Also, deadlock is also challenging to deal with, where we end up potentially unexpectedly in the situation where, and we all know this one, where thread 1 has one lock and thread 2 has the other lock, and they both require the other lock at the same time, and while they're waiting, they effectively hang forever because there's no thread that can make progress to release the lock that's in the circular loop. Okay, that's just last term. The other thing that makes it hard that you may not have experienced much yet, because you've always been at the low level in the sense of dealing with shared state in the function that manipulates the state, and not really built too much of a system that's much bigger, and that is synchronization doesn't necessarily abstract. Okay, what we've got here is two modules, and the modules work independently correctly. So with module A, it's basically got some kind of state in it. Every thread that calls into it manipulates that state needs to grab the lock associated with that state. So thread 1 would have to grab the lock associated with module A, and if thread 2 calls in there, it has to grab the lock as well. Okay. Independently, module B is one of these sort of, I'm going to go to sleep waiting for somebody else to do something modules. So in this particular module, a thread that calls in this case thread 1, would go to sleep waiting for thread 2 to invoke the wake up within module B to wake up the thread that's gone to sleep. So independently, these two modules work perfectly. Okay, thread 1 can call in and go to sleep, thread 2 can call in and wake him up. Likewise with module A. Now if we compose these two modules together such that module A calls module B, we've built a broken system. Okay, because thread 1 calls, grabs the lock, goes to sleep. Thread 2 calls, grabs the lock. It's never going to get released. And so therefore thread 2 is never going to ever get into module B to wake up thread 1 to release the lock. Okay, circular dependency. Callbacks don't work with synchronization. So if you think about if we've got module B and module A, and they both independently have their own state and their own lock, thread 1 calling in the normal direction effectively defines a locking order, module A then module B. A callback, by definition, goes in the reverse order, and so thereby has the locking order in the reverse direction. And we all know if we don't have a consistent acquisition of locks, we're deadlock prone. Okay, so callbacks don't work when we compose things like this either. Okay, so synchronization ends up being hard in large complex systems. More cases. Getting good performance is hard with synchronization. Okay. And this is an area that we didn't really focus on in the base course, but there's a trade-off here between, let's keep locking simple. Okay, and what I mean by simple is coarse-grained locks. For instance, let's have one lock for the entire software system, for the entire operating system. Our life is super simple now. There's no deadlock, there's no race conditions because we always grab the giant lock. Okay, but that might be simple, but that leads to really low levels of concurrency. Only one activity within that large operating system lock at a time. So if we've got OS intensive workload, we're only going to keep one CPU busy because we've only really got one core can be in the operating system at a time because we've got such a large locking granularity. Alternatively, we could go for high concurrency to get good performance across multiple cores by having fine-grained locking, but fine-grained locking increases the complexity, provides all that opportunity for deadlock, and having to understand locking orders and depth and what's going on in functions that you call. And it also reduces the performance in the common case because you've simply got to grab and release lots of locks for manipulating the different parts of the operating system, even if there's no chance of a race, okay? Because you have to be conservative with lock acquisition. And there's also the whole switching between different lock holders and context switching overhead, etc., that also limit the overall performance. This one's not so true anymore, but it's probably true for you in the assignment, given the low-level environment that you're working on. Okay, threads were not well supported back in the 90s. Okay, if you're talking PC, this is pre-Windows 98. Okay, so we're talking DOS. Okay, yeah, so threads weren't very well supported on a DOS box. Okay, Macs didn't support threads at application level either. This was OS 9 level, sort of like the cooperative multitasking Mac, I think it was at the day. I can't remember, but it was pre-protected operating system. Mac variant, that's for sure. The standard libraries of the day were not thread safe. So if two threads of a thread library called into libc at the same time, there's a whole bunch of races in there because no one thought that you would need a thread safe C library because no one had threads. Okay. The kernel calls weren't multi-threaded. For instance, the error number in the C library would get overwritten by the last system call that returned from the last thread calling into the OS. And there were no debuggers that actually understood threads. Okay, so we're making our life more difficult using threads. There's a whole lot of complexity. They're not very well supported. And more importantly, we don't really want concurrency in the first place anyway because we're on a single uniprocessor in the first place. So the alternative, event-driven programming, one execution stream, no CPU concurrency. One model of an event loop is handlers register a callback that the event loop calls. So that's kind of another slight variation of the event model. I sort of effectively talked about the giant switch statement with the handlers for each event type. The more dynamic event model is handlers basically register for event types that they're interested in, and they get a callback from the event loop. Okay. So event loop waits for events, calls the appropriate handler. There's the important bit, no preemption of the event handlers, and handlers are short-lived. Okay. So what are events used for? Well, at the time, mostly for GUIs. There were a few GUI toolkits that mostly focused on events, with having an event handler per button instance on the screen that would get invoked if you clicked. Okay. And distributed systems of the time that went to the trouble of using asynchronous I/O in order to allow the event handler to overlap I/O with computation. They'd end up having one event loop per machine in a distributed system that would explicitly overlap I/O with execution. Okay, so what's challenging with events? Okay, so this is one that's worth focusing on. Long-running handlers make applications non-responsive. Okay, the latency of a handler reacting to an event is largely the latency of the longest handler that may get invoked. Okay? So if we've got a handler that wants to run a video in our GUI, how do we manage that? Okay? So the idea is here, basically, run a uniprocessor Unix model without necessarily threads. Well, fork off a sub-process that just plays the video to a sub-part of the screen just for that one bit, okay, and then get an event to find out when it's finished. Or break up the handlers into multiple parts where we rely on asynchronous I/O, where the first handler schedules or makes the request, and then we'll get an event for the second part of the handler saying, whatever the first part asked for is now ready, you can continue finishing the event. The other thing is you can effectively call back into the event handler or return back to the event handler, the event loop prematurely in order to make a little bit of progress within an event handler, but give other event handlers a chance to run. Okay. The other challenge is we can't maintain local state across events, because remember, as soon as we return from the handler, the local variables are gone because the stack's been deallocated for that particular function invocation. Okay? So we have to explicitly identify any state that we'd like to persist across the handler and move it out onto the heap. We have no real CPU concurrency, so if we're really aiming to keep CPUs busy, then events aren't really what we're looking for. And event-driven I/O at the time was not really well supported. Okay? And I can't remember the specific write buffering scenario that John was talking about on this slide. However, if you compare the two, events avoid concurrency as much as possible. Okay? So they're easy to get started with. Okay? There's no concurrency, no preemption, no synchronization, no deadlock. It's sounding good. We only use complicated techniques for effectively the boundary cases or specific cases where the event model has an issue, like say a long-running handler or blocking. Okay. With threads, even the simplest application faces the full level of complexity. Once you've got threads and shared state, you've got concurrency, you've got synchronization, even for the most simplest example. Debugging with events is much easier. Okay? Timing dependencies are only related to the events, not any internal scheduling that you have no control over. You've got a single flow of control that you can sort of trace through with the debugger to see what's going on. With threads, it's really hard to reproduce the problem because you don't control the sequence of events that created the problem. And so it's much harder to track down something like memory's corrupted in a strange place and I don't understand why, versus something's a bit slow when I call the event handler. Let's trace through it and see what's delaying it. So events can be faster on a single CPU. We've got no locking overheads, no context switching compared to a thread model. They're more portable because, hey, they're just a switch statement on here's an event type. For each event, call the appropriate handler, or could even just be a jump table. Okay, so that's very easy to port to different operating systems without having to worry about whether the system is POSIX threads, some other threads, whether I have to come up with my own user level threads library, how that works with the existing system call interface. At the time, it was quite challenging because there was not a standardized user level threads environment. Now the two big differences are probably just POSIX on Unix-like systems versus Windows threading. Okay, so the advantage of threads, though, long-running stateful handlers, okay, without freezing the rest of the system within the handler, and scalable performance on multiple CPUs. Okay. So should we dump threads? No. When we really need an execution model to keep threads busy, to keep a machine with multiple CPUs busy, then there really is no alternative than to have a model that has at least a thread per CPU. So large applications that are on big machines that have multiple CPUs need a thread-like abstraction that allows the operating system to be able to identify activities that it can assign to CPUs to keep the machine busy. However, concurrency is still hard, and the argument here is we should avoid it whenever possible. Okay? If we don't need to hurt our brain thinking about concurrency, then why do it? Okay? Threads are more powerful than events. We can keep a machine busy, but the power is rarely needed is the argument here. Okay? Threads are much harder to program, only for experts. Events are much easier, implying that a broader range of programmers can deal with an event model much more easily than a thread model. So you use events as the primary development tool. Only use threads for performance critical cases where you really need concurrency across multiple CPUs. So, any questions? No. So have I discouraged everybody from ever looking at threads again? No? Good.
I want to be a wizard.
So we should probably take a break. I kind of kept going through the usual break. I am probably largely on schedule for the next talk after this one. So let's take a break for a little while. You can grab some caffeine at a strange time in the day, given it's a bit after 5. And we can pick it up in a few minutes. Okay, so I previously made a case that threads were a bad idea, so I'm now going to hop on the other side of the team and present a paper that tries to make the case as to why events are a bad idea. And the nice thing about doing these two back to back is it largely gives you a good indication of how to relate the two models together and the strengths and weaknesses of both. Okay. So this was a talk, would have been 8 years after the original talk, in a workshop called Hot Topics in Operating Systems. And so the world had changed from 1995. Okay, this is largely at the tail end of the dot-com boom, where the whole world had just spent its entire time on figuring out how to make a fast web server, because everything went online in the late 90s. Okay, and so there was a lot of work on how to build web services that were efficient and could effectively operate what they call near the knee. Okay, and so I'll spend a bit of time talking about the knee, because the knee is actually something worth knowing in general, beyond more broadly than what we're talking about today. So what we've got here, is a performance graph, where this is the typical sort of graph of offered load along the x-axis. So the further to the right we go, the more load we're attempting to have the box perform. Okay. So you can think about this as the number of clients that keep being added to a particular web service. Okay, and up this side, we've got the amount of performance, i.e. might be responses per second or something similar, that the web server can perform on this particular bit of hardware, software configuration. Now, typically, as we increase the load, we increase the amount of responses that we get because we've simply got more things to do, so the performance rises. Now, in an ideal world, at some point, the machine becomes saturated and simply can't perform more operations per second than what it can perform when it's running flat out, independent of how much load we keep throwing at it. Okay? Now, the ideal case is great if that's the way your system works. Okay, if your system works like that, you've built a really good system. Okay, and the reason why you've built a good system is most normal systems end up getting to a point where some kind of resource ends up resulting in the system thrashing in the virtual memory sense, or it may result in shall we say, doing work to process a request, realizing I'm overloaded, throwing that request away because I can't deal with it because I'm overloaded, starting the next request, processing that, maybe finishing it, starting the next one, or throw it away. And so the more you overload, the more you end up partially processing before you throw it away because you're overloaded, which then means you've got less computation time to process the stuff that you are successfully processing. It ends up being this negative feedback loop where you end up falling off this cliff, i.e. going over the knee, and your performance drops off once your load ends up going beyond a certain level, which in this particular diagram is here. Okay, so ideally, you'd like to be able to operate near the knee. At some point, you'll probably drop over it. But in an ideal world with a good design system, this curve will go further out in that direction and postpone the thrashing and dropping off the curve. Okay. So where are we? So we're trying to develop these highly concurrent, high performance concurrent applications, big web servers on big boxes that want to support the maximum amount of clients. Concurrency is really hard. There's lots of race conditions. It's hard to write a parallel server. To make scalability perform well, we'd like to have no order n operations. And what I mean by that is that as we increase the amount of load, it shouldn't take longer to process a request. Okay, so a request should remain the same level of complexity to process, independent of how many requests we're getting at the same time. Okay, we just process them one at a time. It shouldn't make a request twice as long just because we've got 16 requests running. Okay. There's also scheduling issues where the allocation of resources or how the scheduler behaves may improve or decrease the performance of the system. Eventually things will get overloaded. Code complexity makes concurrency also hard. So this was the situation when everyone was trying to basically build software infrastructure to support web services. Was there a better way of doing this? So this boiled down to a debate in the community between threads versus events. Okay. So what I've got a graph here is ease of programming, performance. Performance meaning scalability on large machines. Okay. So with a thread programming model in red, if I use really coarse-grained locking, okay, it's a really simple programming model. It's easy to deal with. There's not many locks. However, the downside is that the performance is really low. I can't scale very far if I use coarse-grained locking. So if I want performance with threads, okay, up here, I need to use fine-grained locking. Fine-grained locking introduces a whole lot of complexity, so the ease of programming is now back down here. So with threads, I've got one or the other, was the claim. Now, the observation or the claim at the time was that event-based models could give us better performance with an ease of programming that was easier than fine-grained threads. Better performance in fine-grained threads, easier programming. Okay? So the question is, how do we get both performance and programmability even better than these two options? Okay? And the other question that also pops in here is, are events fundamentally better than threads? Because it appears so at this particular point. So the position of the people giving this talk was that, something that I will introduce in a moment, the assumed knowledge of this talk is all operating systems researchers, okay? So that's why the talk is at a pretty high level of assumed knowledge. So thread duality is the observation that you can transform a thread model into an event model and an event model into a thread model with the simple transformation between the two. I'll introduce the details of that in a moment, but that's probably enough to understand. So they're arguing is that they're largely the same, but threads are better, and I'll make an argument why after we've seen that whole half an hour talk on why they were not, because they're more natural to program, okay, and they're a better fit with current tools and hardware. Notice we're 8 years later, where threads have become well supported for applications on all the modern operating systems. And they're arguing to get the performance of events in a thread-based system, it's really all about compiler and runtime integration. Okay, to use the similar tricks that the event people were using in the context of a thread system, given that they should be equally applicable, because the thread event duality should still hold. Okay. So let's have a look at the duality argument. Okay. So the assumption here is that we want to follow good practices in building a system in both models. Okay. This is not a debate about I can do really weird things with the event model that I can't do with threads, or I can do things that are particularly appropriate for the thread model that are harder than events, but that's really obscure. The idea is that if I want to build a simple system, and the simple system here is a web server, funnily enough, the web server is a simple control flow that accepts a request, accepts a connection from a new client, HTTP request, reads that request, looks in the cache, because it's keeping an in-memory cache of the things that it's returning back to the clients. So for instance, all the images on the web page that it's serving, it's keeping them all in memory, and it looks up in memory to see, okay, do I have image.jpg? Yes, I do. Shovel it straight back, i.e. write the response, and then exit. Or if it's not in the cache, read it from the file system into the cache, and then write the response back to the client so we can print it on your web page, in your web browser, and then exit. Okay? So the claim here is that the major concepts between the two models, and I'm going to go through it in detail because the next couple of slides animate, are analogous. The structure ends up being the same, so shouldn't the performance, given good implementations, be similar? Question. So let's take a look. So if we consider each of those boxes as just a chunk of code that implements that functionality, like accepting a connection from the socket, decoding or reading from the socket, and then decoding what it is that we need to do in the read request, looking up in the cache, do we have it? Maybe reading something from the file system, writing something back onto the socket, and then returning back to being ready to accept the next connection. If we're trying to run all these things potentially in parallel, then, but not have concurrency within each of those circles, then in the thread model I can use a monitor. Okay, each one of those is declared as a part of a monitor, no concurrency inside it. All the local variables and shared state within the monitor is fine. Or each of those particular circles ends up being an event handler with a queue of events posted to it. So read request just sits there processing, hey, I got a new connection events. Okay. The functions that are exported by the monitors are effectively the entry points into the monitors. They are equivalent to the kinds of events that are accepted. So read request probably only accepts a new connection event from the accept connection component. Okay, the pin cache thing probably only accepts, here's a request of a particular, for a particular thing kind of request. Okay, so we can transform the different event types into the interface of the particular monitors, or we can take the monitors and transform the functions they export into particular events for handlers. Okay. Oops. Both of these styles of execution models allow us to construct things like call return or fork and join, where I fork off a bunch of work and I wait till it's all finished before I continue. You can construct similar kinds of things with sending a message and awaiting a reply from all the people that you sort of kicked off with a message. Okay, so there are direct analogs between both models. Okay, so given there are direct analogs and I can kind of take almost the same code and put it into the separate frameworks and have it work, why is the performance, why are there such significant performance differences between events and threads? Okay, so at the time everyone was arguing, because one of the research areas was basically building event-based web servers, that events had lower runtime overhead because there's no synchronization, better live state management, and what I mean by that is that they only have a single stack, so they don't leave stacks lying around containing state that's needed in the future when things are suspended. Okay, they're more compact, use less memory. Effectively, the only live state, i.e. memory that's still going to be used in the future, is basically managed explicitly by the code. Okay. Synchronization is inexpensive because it's largely non-existent. Control flow is more flexible because with the event-based model, you can effectively post any event to any event handler, from any event handler, if you really wanted to. And as we'll see, you can do some more scheduling tricks with events that hadn't been tried on threads. So the argument here is that there should be really no inherent problem with threads, and that thread implementations had room to improve to use some of the kinds of techniques that came naturally with events in the context of threads. Okay, so they wanted to do an experiment comparing events versus threads. Just a really simple one, because this is actually a workshop paper, not a mature conference paper. So largely the way workshop papers work is that you want to make a potentially controversial point and opinion, back it up with some data so that you can have a debate with the community at the workshop regarding your opinions and get feedback, etc. Whereas conference is much more mature. You've basically got a scientific result and the evidence to basically back up and validate your result. Okay, so the point here is not to claim that threads and event-based servers are exactly the same. What they want to do is do a simple experiment to show that, at least for this particular example, it actually came out pretty close. Okay, so what they did is they took the GNU pthreads library, okay, and they modified the threads library to avoid order n operations, which it had in there, and do a little bit of optimization on the context switching overhead, okay, and using a model that had a thread per task in this particular benchmark, and task meaning activity, which would be largely the parallel to an event-based model, which would have had an event handler dealing with each incoming task, okay, and they basically built these two servers, compared the two by having a number of concurrent tasks issue requests, measuring the performance of requests per second that they got, and you get the typical kind of curve with the knee here that rolls over and goes flat. The threaded server is in blue, the event-based server is red, and the point they wanted to make here is that they're largely the same. Okay, why at the time were people building event-based web servers getting so much better performance than the existing thread-based web server? Okay, the thread-based web server at the time was basically Apache, and people built a whole lot of small alternative web servers to basically compete with Apache that were event-based, and they were getting much better performance than Apache. Okay, so the live state management is, if we have a look at the state management in an event-based system that exists when an event has to end, but we need to store some state to effectively continue this activity in the future, then that state has to be stored out onto the heap. So effectively, this is storing some kind of continuation out into the heap to get picked up by another event in the future in order to be able to continue from where the previous event managed to progress to. Okay, so by explicitly managing the state like this, we avoid, hopefully, saving lots of extraneous state, because we're only really saving the state that we need in the future, not all the state that happens to exist at the time. Whereas the thread-based model, when you call a function, stuff gets allocated on the stack. Okay, I've got some leftover scribbling from last time I did this lecture. Apologies. We can see that all the variables allocated inside this stack frame, and there's what, 5 of them, some of them will be needed in the future, the green ones, and some of them are not needed in the future, okay, but they're still there on the stack, okay, because the one that we need is the one at the start of the stack, and the one that we need here is at the end of the stack, and we can't kind of compress and move stuff around on the stack because the compiler's generated the layout where the variables actually lie. So we end up using more memory because we've had more variables, but we only need some of those variables going into the future, but the stack's already allocated. Okay, and the stack will have multiple of these stack frames as they're called. Okay, so what can we do about that? Well, the idea is we should really fix the compiler to be smarter about this. We should do better analysis of the variable usage by the compiler to identify what would be dead at various points within the function, so that if we get to the point where we're suspended, this live state is basically, this dead state is down on the lower part of the stack, and the live state is basically at the top of the stack, so we can shrink the stack to only really contain the stuff that we still need in the future. Okay? So we can do better planning and management of the stack and try to get some of the advantages that events had of doing explicit state management. Okay? Synchronization. So one of the advantages of the event model was that there is no synchronization because there's no concurrency, or there's very limited concurrency, because what they would have been doing here is running an event loop per CPU, okay, relatively independent of each other with little shared state. So the argument here is, okay, let's just do cooperative multi-threading within the process, just like events do. Okay, and just like events, this presents the same kinds of problems that we have with events of basically unexpected blocking, supporting multiprocessors, if we're just doing cooperative multi-threading, effectively user-level threads within the process. But all those problems exist with events as well. Okay. So we can apply the same kinds of solutions that the event-based people do in the threading context. Okay. The control flow argument. So it's true that events are more flexible. You can build crazy relationships, posting events in different to different event handlers in strange orders, but in practice, programmers don't do that. Programmers like to keep things relatively simple with call return. This one here is fork and join. We have multiple worker handlers, basically reply when they're done, or build pipelines, one after another. So there's some sort of standard structures that people tend to use, whether they're in the event-based world or the threaded world. So complicated patterns, which is perceived as an advantage of events, are basically likely to cause bugs, harder to understand, and unlikely to be used anyway. So it's not really a good argument in the debate between events versus threads. Scheduling. This is an interesting one, and I wish the slide wasn't so messy. I should have cleaned this. Actually, I'll clean it now. Why not? Review. Where are we? Delete all ink in the presentation. That's better. So, without getting into a huge amount of depth, again, the assumed knowledge here is pretty high. One way to look at this diagram is that this is progress through an activity. Okay? So this might be the accept connection, read request, send something back, and then exit. Okay? So you can view this diagram as either a thread-based model going from start to finish, where this basically executes one after another, versus an event-based model, which, if you observe, each of these circles is running the same code. Okay, so this would be a parallel thread, running effectively the same code. In the event-based model, this would be the same handler running one event after another, okay, doing the same thing. So this is the same code, basically receiving the request, same code receiving the next request, same code receiving the next request. Now, the observation that the event-based people made was that if I've got a single piece of code processing one event after another, then the cache locality of this code becomes an advantage because I end up loading up the cache when I process the first event of this type. And then when the second event of the same type comes in, the code's already in the cache and I'm running full speed. Okay? So one of the observations that the event-based community made was that I could do what was called 2D scheduling, where what they would do is process all the events of the one type first, and that would run relatively fast. Then they'd process all the events of the next type, and so that would end up having to load the cache for that bit of code, but the rest of these events would run much faster. And then I'd schedule all the events of the next type. And so that they were arguing improved performance, allows batching of a particular event type. It provides better cache locality compared to running all this code, then giving the next thread a chance to run and running all this code, and then giving the next thread a chance to run and running all this code. Okay, you can see the argument here. But the point here is that you don't have to do this. One could actually track where threads location currently happens to be and use the call graph to predict which threads should be scheduled next based on where they currently were in order to try and get some of the benefits of this 2D scheduling. Okay, so there, instead of having the event-based system basically process an event type at a time, try and have the thread runtime identify thread progress in order to try and get the same kinds of benefits, which you can imagine would be very difficult to do. But like with most runtimes like, I don't know, the garbage collector in Java, it's exceedingly complex to build correctly, but once it's done and it works, everybody can leverage it. Okay, so that's one of the things about building low-level systems and infrastructure like operating systems. Yes, they are complex, but once you've got a correct, well-performing system, everyone benefits. Okay, and then you don't have to keep changing it, hopefully. Okay, so I largely did that with diagrams, threads versus events. Okay, so proofs in the pudding. So what they did is to do a fairer comparison. They built a web server because everybody was building web servers at the time, and built a user level threads package, which was a subset of the pthreads package that existed at the time, POSIX threads. They intercept blocking system calls to try and provide asynchronous I/O to avoid that problem of blocking one user level thread in the system blocking everybody. Okay, so they intercepted the blocking system calls to use asynchronous I/O to avoid blocking. There was no auto-end operation, so independent of the workload of concurrent clients, the scheduling algorithm in the user level threads library was auto-one. Okay, they support over 100,000 K threads. So the idea here would be, okay, 100,000 concurrent requests. Each thread processes its own request independently. Fork off a new thread for every new incoming thread. Incoming. It's end of 2 hours. Every incoming request. That's the word I'm looking for. And it was about 5,000 lines of C code in their little threads package. They built a simple web server that they called Not. Remember why they called it Not. Feel free to have a look in the paper, they may actually say. And they wanted to compare that with Haboub, which was one of the popular event-based web servers that was around at the time that showed much better performance characteristics than what Apache did. And so it was one of the motivators for the argument that events were better. Okay. And if you have a look at this, and they're not arguing that their web server is a, shall we say, a production-ready, mature implementation, but they were arguing that it's enough to sort of say, okay, the purpose here is that the research is worth pursuing, not that they built a mature system that beats the existing systems out there. So what they did is built an immature system that did beat the existing system out there for the limited functionality that they probably tested. Okay, so Haboob is the red one. It was event-based. And then there was two variants of not. There was not A and not C. Not A favoured accepting new requests whenever one came in. Okay. Whereas not C favoured completing existing connections rather than accepting new ones. Okay. Now this is a really nice example of the performance problem that I talked about earlier. Okay. So if I favour accepting a new connection, I'm going to do work, expend computation, getting a new request, doing something to interpret what's going on. Okay. And once I'm overloaded, and drop off the end of that performance cliff, the work that I've used to accept that connection and kind of partially figure out what's going on but not finish it ends up reducing the amount of CPU available to process the existing connections. Okay, and so the more new connections that come in, the more CPU I end up wasting accepting new connections that never finish. And the worse this performance drop-off ends up being. Okay. Now, if I favour existing connections, what ends up happening is that the connection, incoming connection, will get dropped inside the operating system, inside the IP stack, or inside the device driver, or even in the extreme, in the hardware at the network level. Earlier in the software path than when it finally gets to the web server. Okay, because the web server is not grabbing the new connections from the socket layer fast enough, so it's going to push the congestion further into the operating system, and depending on how the operating system favours connections, it may push it to the device driver. And depending on the DMA ring buffer inside the Ethernet card, you may push it to the level where you fill up the ring buffer and it just starts dropping packets at the hardware level. Okay, so the point here is that the general idea is that if you're going to have one of these situations where you might fall off a performance cliff, it's better to drop the work earlier in the processing of it rather than later. If it's likely that you're going to end up dropping packets or dropping work that you can't process because you're overloaded, the earlier you do it, the more processing you're going to have left over to actually complete the other stuff that you're working on. Okay? And so this graph is just a huge example of exactly that. Because favouring existing connections will have the OS doing the dropping, and so it's managed to have closer to an ideal performance plateau than the case where we favour accept and we drop off the cliff. So, how are we doing timing-wise? Oh damn, I'm going too slow. So the argument here is that this might all work if we manage to build this better runtime, but their argument, and this is kind of important, is that threads are better and more natural to program. This is really what I want to show you. Why? So here's our example where we've got a thread implementation on the left, where it's just a function, thread main, allocate a session, accept a connection, read a request, pin cache, write the response out the session descriptor, and then unpin something, okay? Pin cache is basically pins, whatever it is, that we're going to send in the cache. If it's not in the cache, then we read from a file. Okay, that's pretty easy to understand. Okay, it's not necessarily meant to be syntactically correct, just to give you an outline of what's going on here. If we look at the event-based model, we've got an accept handler that basically creates a session and posts an event to the request handler. The request handler posts an event to the cache handler. The cache handler pins the session, and if it's not in the cache, it posts a request to the file handler. Otherwise, it posts a request to the response handler, and so forth. Not all the code is here. And eventually the exit handler will get an exit event. And so you can see the parallels here. Okay. So these are the same. It shouldn't be, why is one might be more difficult than the other? Well, follow the events. Okay, it's the same code. The previous code was largely manually ordered in the same way as the thread model in order for you to be able to follow it. But there's nothing about the event model that encourages the programmer to ensure that it's in a way that's readable to anybody else other than him. And even depending on the level of complexity, it's probably going to be hard for him to follow. Because here we're sort of going from accept up to request, up to cache, and back down to exit eventually. Okay? So threads, what you see is largely what's happening in the order that it's written. In the event handler model, yes, within an event handler it's in the same order, but how the events relate to other event handlers is kind of completely opaque to how it's written. Okay? Dealing with error conditions is very challenging. In the thread model, we get automatic cleanup because once the function exits, anything allocated within the function gets cleaned up. Okay? So if I return early, that session gets deallocated. Okay? If I get pinned, the unpin will follow up. It happens in that order. Okay? If I look at the event model, if I return from the cache handler and don't end up following the right flow, I may end up in the situation where if I go straight from the request handler to the exit handler the request handler to the exit handler without going through the cache handler, I may unpin something that's not pinned, and that might just be a complete bug that crashes the code. Or, if I don't end up in the exit handler, because I've come out through some other exception path, okay, then I may not end up freeing something that's allocated earlier on in a different event handler and sort of passed around on the stack. So we get some implicit allocation management by using a thread model with local variables. Okay, that you have to explicitly manage in the event model. Okay. Yeah, that's largely what I've already said. So there's lots of existing infrastructure for threads now, as opposed to when that original talk was given of where threads were a bad idea. GDB understands threads. There's lots of languages and compilers that provide more manageable thread abstractions and more help for concurrency management. That's not true in the environment that you're programming for the project. Okay. I won't say you're back in 1995, but all low-level embedded work where you're largely building the tools and the environment that all these other things are built upon basically means that you're working with fairly low-level primitive environment that makes life easier for people that come after you. Okay, that's just the operating systems or the embedded systems world. Okay. So the consequences for writing application level threads is that they're more amenable to analysis and less effort to get working systems. Wow, we're contradictory to the previous talk, aren't we? I'm not going to delve into this part in depth. Okay, there's too much assumed knowledge for me to convey what particular techniques that they're talking about here. Okay, so I'm just going to move on, other than to say that they believe that they can explore particular performance optimizations that worked well in Hadoop in the context of a runtime environment for application level threads. Yeah, so they have a research agenda, and this turned into a paper in one of the major conferences where they got a good result for a thread library that they built that provided performance similar to event-based systems. It's called Capriccio. So, conclusion. Threads are kind of like events. You can transform one into another. Similar performance, similar expressiveness. Okay. Their argument is that threads are easier to deal with than events in terms of complexity and manageability. Okay. And that they might be able to get the performance and the ease of use of events by improving compilers and the runtime environment that manage threads. So the question now becomes for you, which of the two models are you going to use for the project? Because largely it ends up being sort of two worlds. One is that you do something that's fairly event-based and end up using continuations in the cases where you need to suspend execution on behalf of one request and pick it up later, okay? Versus using threads and sync primitives on top of SEL4, okay? One thing to observe about the project is that despite what it looks like, it's not actually that complex, okay? It's probably, it's simple enough that the choice between threads versus events is relatively unclear. Like if it was a really simple system, it is be obvious, okay, just use events, okay? It's not worth dealing with concurrency in threads. If it was a really complex system with lots and lots and lots of code, more than we'd expect you to write in a semester, then it's pretty clear that moving to an event-based model, a thread-based model, is probably the right way to go. Okay? So you're kind of at the boundary where you can choose between the two. Another thing I'll throw out there is people have found things like coroutine libraries on the internet and ported them to their project and used a coroutine kind of environment. So PyCoro ended up being popular some years. Different years do different things, and I don't know whether it's people hanging around in the lab just going, oh, I got this idea, and everyone jumps on the same idea and they all do something similar. I'm curious how it goes this year. I'll give you some stats, I guess. It seems to be more common that people start out with events for the reasons given on the original talk. Like get to the point where you kind of understand what you're doing, where the pain point happens to be, and then choose to transition to threads or choose to implement a continuation-like construct retaining the event model. Okay? Versus starting with threads, that is less common because then you effectively have to build the whole thread infrastructure and how you're going to manage it before you even write the first system call implementation inside. Okay, you've got to understand how to piece it together. Okay, so your call. I'm hoping I've given you way enough context. Any questions about the two talks, actually?
Remind me again when this one was?
Sorry?
2003.
Yeah, 2003. Yep. It may seem like a long time ago for some. It's probably almost getting the point where, I don't know, people born after this? It's almost getting to that point.
Not quite.
Not quite.
They're in year 12 or first year.
Yeah, they're in
My
first.
brother's in year 12.
Yeah.
Get some next year.
Yeah, I'll get some next year. Yeah.
Well, we're all born after the 95s.
Yeah.
Most of us.
So I'm hoping I'm giving you a little bit of history of computation and how things are going in addition to the low-level OS stuff that you will need probably in general if you end up writing a runtime or building a low-level environment. It's really good to understand the trade-offs between these two. Okay. Yep.
So do current embedded systems still commonly use event-based systems?
Yeah.
Or?
Yep. If you write a washing machine controller on a microcontroller, you're going to be using it event-based. Okay. And in fact, know of a company that built medical devices that just transitioned into a thread-based system from an event-based system in recent years, and that was largely the complexity of all the features of, we want Bluetooth now on our medical device. Okay? Whereas previously it was like, it must work, and it was relatively simple, and now they're sort of suffering the features that people want their phone to control their medical device, and so they've transitioned into an environment that can basically support more complex code.
So do you think embedded system more will support thread-based systems? Or?
No, I think my opinion is that it will remain the same in the sense that simple systems will keep it simple, and complex systems will use more complex techniques. It's just that more things that were traditionally simple will become more complicated. Things like, I don't know, the classic example is the internet refrigerator. Like, why? Okay? You've transitioned from a little event-based controller that keeps the temperature of the fridge at the appropriate level to something that runs a web browser on the front of the fridge. Okay?
Why is the right question?
No comment. Okay, so I'll see you in a few weeks' time because I think Kernel's back next week.
Okay.